First of all, to the organizer for their kind invitation. It's really a pleasure to be here and to discuss a topic that received a lot of attention in the past and that might be revived in the near future. This is the topic of quarkonium production at low energies. So as you know, if I can succeed in switching my, which usually, let's go with the mouse. Okay, even easier. Okay, so as you know, quarkonium is the only, let's say, real hard probes that was studied down to low energies in nuclear collisions in the past. And the results in nuclear collision came from a series of experiments that took place at the SPS. These were in a row, NA38, NA50, and NA60. And since the role of cold nuclear matter effects is important, it is also stimulated an experimental program which extended, let's say, beyond CERN to Fermilab and to HERA. The results, of course, available were on the states like the JPSI and the PSI-2S. So I would like, let's say, first to briefly recall the experimental techniques and also sketch some of the main results. But then I try to go to the points that remained open and that would justify, let's say, near future measurements in nuclear collisions. These could take place at FAIR in an energy range that, as discussed this morning, is very close to threshold, but also in the regime of the low SPS energy, where the NA60 Plus project is preparing an experiment which is devoted also to that. So this is just to give you a more, let's say, detailed idea of the time scale and of the energies of this experiment. So the energy range for this fixed target experiment was, let's say, no larger than 20 GeV, and experiments took place until 2003. Since here, let's say, maybe not everybody is familiar with this kind of results, let me just sketch very briefly some differences for what concern quarkonium production between collider and fixed target energies. So for what concerns charmonium, at collider energies, the results are compatible with the observation of a suppression, which is counterbalanced, or even, let's say, more than counterbalanced by regeneration process. On the contrary, at lower energies, one rather looks for suppression effects if existing, and due to the low charm core multiplicity, there is basically no regeneration present. And then one has known hot matter effect, and so shadowing is, let's say, situated in two different regimes. At the LHC, one is more or less deeply into the shadowing region with values of shadowing which are well below 1, while in the region where fixed target experiments sit, this is more in the region of moderate anti-shadowing around x equals 0.1. And finally, this is also very important at LHC, the final state breakup effects, these are completely negligible because the crossing time of the nuclei is extremely short, while this was absolutely not the case in the fixed target environment, where this crossing time becomes long and the breakup in the nuclear matter can be sizable. Let me just start by, let's say, flashing this slide, which also shows some of the main issues in this kind of measurement. Indeed, the suppression of the JPSI was first observed in collisions of oxygen on uranium, and one could see in the ratio JPSI over continuum a decrease from peripheral to central events. On the other hand, it was realized very soon that if you plot these kind of ratios as a function of this L variable, the mean thickness of nuclear matter caused by the CC bar pair, then let's say there is practically continuity between proton nucleus or nucleus, and these seem to imply that, let's say, there is a significant effect of the suppression which is due to the cold nuclear matter effects, and this stimulated indeed an intensive program also for what concerns this collision. But from history, let's say, to the final, let's say, result on this topic, this is basically a summary plot of where we are in this regime. So here, as a function of the number of participants, one can plot the ratio between the measured yield of JPSI and what one would expect from extrapolation of cold nuclear matter effects. And for these specific, but also for other studies, the Drellian reference was used as a normalization for the JPSI. And the results, let's say, imply that these suppression effects beyond cold nuclear matter reaches about 30% in central LL collision, which is qualitatively consistent with the suppression of the feed down from the Psi2S and the KC mesons. The indium-indium results show the, let's say, smaller uncertainties, mainly because of a different analysis approach. And anyway, the global suppression observed was very small. There was this kind of wiggle at intermediate centrality that remained unexplained, for which there were some, let's say, explanation in terms of coupling to the X3872 via the DD star, and this was proposed several years ago, but honestly, this was never, let's say, brought to full maturity as a kind of explanation. So we were talking about Drellian as a reference, and this was done let's say, basically because of experimental reasons, because if you make the ratio of two measurements which feed inside the dimuon mass spectrum, then you cancel a lot of uncertainties. But then Drellian is also a hard process, insensitive to the Quark-Gluon plasma, and so this ratio is proportional to the JPSI yield per nucleon-nucleon collision. This modulo the fact that, let's say, shadowing effects on Drellian and JPSI might not be exactly the same, because one is quark and the other is gluon, but let's say it was a clearly decent and proper kind of normalization, which had anyway the disadvantage of a low Drell statistics, especially in the region of the mass spectrum where one would, let's say, have the possibility to fix this contribution. So this was the reference that was used, and we have said that cold nuclear matter effects could play an important role, and this kind of plot shows that if one uses L as a scaling variable and then plots, for example, all the a sample of proton nucleus results obtained on various targets, one sees a clearly exponential behavior, which implies that the breakup effects are dominating. This exponential behavior extends to intermediate mass nuclei, and finally it is broken for a heavier collision, and this is what is was normally called as anomalous suppression of the JPSI. There are, though, various caveats, because, for example, in this plot, let's say data at various energies were mixed, and so this assumes, in a way, an independence on square root of S of these cold nuclear matter effects. And also this exponential kind of fit assumes that nuclear breakoff is dominating, while shadowing has to be taken into account. So due to this fact, let's say this stimulated indeed a lot of measurements at various energies, including the energy of the nuclear beams, performed by various experiments. And without going too much in the detail, this shows that, let's say, PA results at fixed target is indeed a very complex environment. Here, you can see as a function of the parameter alpha, which is simply a parameterization of the cross-section in nuclear collision as the proton-proton cross-section times the mass number to the power alpha, one sees that there is a significant variation as a function of XF with strong decrease when one increases XF. And also at fixed XF, one sees a stronger cold nuclear matter effects when the energy of the collision decreases. So this clearly has to be a superposition of several effects. We have named the shadowing, nuclear breakup, likely energy loss in the initial states could play a role, especially at large XF. And it is fair to say that no consistent theory description was developed to reproduce this complex environment. So let's say one had to in some way parameterize this result. And here one sees some of the features of this parameterization. First of all, the fact that one sits in a region of anti-shadowing implies that if one directly, let's say, makes a phenomenological fit of the behavior observed in nuclear collision, one would get a systematically lower value for the breakup cross-section than the one that one would obtain if shadowing effects are taken into account. The dependence of square root of S is let's say, very evident here. This is a result from NA60 data taken by the same experiment, which shows that the two different energies, when you study as a function of the mass number of this L variable, the cross section normalized to the beryllium, in this case, a much steeper behavior is observed at lower energies. And that can be parameterized, showing, let's say, as a function of the square root of S of the collision, this increase of the breakup cross section up to values of about 10 millibar, which implies that these effects should become dominant in nuclear collision at sufficiently low collision energy. So to summarize on this first part, let's say with such a result, there is still room for several improvements. First of all, one would like to improve this accuracy for lead measurement, which was limited by the use of Drelian as a reference. One would like to directly access the excited quarkonium state, so the Psi2S and the Chi-C in these collisions, in order to investigate their suppression and study their impact on the feed down. Maybe even more interesting, one could study the energy dependence of this anomalous suppression. This is for top SPS energy, and so one can go, let's say, towards lower energies and see which is the evolution of this effect. There are other variables which could be accessed, for example, the elliptic flow of the J-psi. There were hints already in NA60 in indium for, let's say, an effect in the V2 for non-central events. And finally, also this proton nucleus reference should be measured at the same energy of the ion beam with a better precision, as let's say the current precision at top SPS energy was not very large. It was just 12%. So in order to investigate these and several other questions, we are proposing a new experiment to take place at low the SPS and using beam of lower and lower energies, which for the moment is named NA60 plus. And it could perform an energy scan over the energy range covered for nuclear collision at the SPS. Indeed, quarkonium production was not studied at all below top SPS energy. And so decreasing the square root of S, one could access a region where high mu B effects could become active on quarkonium. For this one, it's still help from theory, since for the moment no real prediction exists. One could study from an experimental point of view the onset of the confinement by looking at the disappearance of the suppression effect on the J-psi, which comes from the Chi-C and Psi2S feed down, and maybe, or let's say more interestingly, correlating them with accurate temperature measurements that could be obtained by thermal dymuons. And finally, also measure cold nuclear matter effects. You can find more details on the project in the web page that we prepared and in the expression of interest that was submitted to the SPS. This is now, I'm not going into detail, this is beyond the scope of the talk, but just to tell you that this experiment is made of a vertex spectrometer coupled to a muon spectrometer for the measurement of the decay muons, and with the possibility of varying the distance of the spectrometer from the target region in order to adjust the rapidity coverage as a function of the energy of the collision. The R&D phase is going on, and let's say here you can see, for example, a first prototype of the toroid magnet, which was built in 2020-2021. Other detectors such as the vertex spectrometer silicon maps, are being developed in collaboration with Alice. For the muon chambers, a collaboration with Weizmann Institute in Israel is now going on. So the idea would be to have some first tests on the beam of these prototypes next year. But let's see which kind of performance could be reached. So the measurement of NA60 in indium-indium collision allowed to collect 30,000 JPSI, and with an intensity that could be reached in the H8 beam, which is the one foreseen for the experiment, which is 10 to the 7 lead ions each 20 seconds, and assuming a proper thickness for the target and 1 month of data taking, one could reach this integrated luminosity and let's say access a statistics from low to top SPS energy, which varies between 10 to the 4 and 10 to the 5 JPSI, which let's say is something reasonable for such a kind of measurement. And by the way, includes a factor 3, this estimate overall suppression that is assumed due to cold nuclear matter plus QGP. So let's say it's relatively realistic as an estimate. Of course, one for the discussion that I made immediately before, one needs also proton collisions to measure these reference for cold nuclear matter effects. And with a beam intensity in protons of about 2 orders of magnitude larger and several nuclear targets simultaneously exposed to the beam, one could aim at a statistics between 5 and 50,000 JPSI. And then by extrapolating this behavior to PP collision, one could then calculate an RP LED and compare it to an RAA. So in, let's say, kind of more modern approach with respect to the Drellian reference. Indeed, this is what is shown here in this slide. So the blue band represents the extrapolation with the corresponding uncertainties related to the statistics from the PA result, and this is a centrality dependence of the nucleus-nucleus results from low to high SPS energy, and with a certain assumption, of course, for the size of this anomalous suppression, which is assumed to be of 20% and to set in at a certain value of the number of participants. So the evaluation could be rather precise down to low SPS energy, and so open the way for systematic study of the evolution of the suppression from top to low SPS energy. How to quantify these hot matter effects by means of RAA, as we have said. And of course, this could be then normalized to the RPA, making a kind of double ratio, and this would be useful to compare the results at various square root of S. The Drellian is let's say, really impractical because of the limited statistics. The other interesting possibility is to normalize to the total charm. And this is potentially accessible via measurement of the hadronic charm. And I flashed just these studies, which were done by Francesco Prino recently, which show that by studying the decays, the hadronic decays of open charm in the vertex spectrometer, and without assuming any particle identification, but just, let's say, a careful set of cuts from the topological point of view, one could reconstruct nicely both the D0 signal from top to low SPS energy, and for the moment also the D sub S, the 3-body decay at the top SPS energy. The D plus meson is also within reach and should not be a significant problem, simply the study has not been done. And for the lambda C, which is more difficult, the studies are ongoing, and it looks like a performance for this meson could be obtained soon. Just another possibility from the point of view of the physics is the study of the intrinsic charm component of the hadron wave function. This would lead to an enhancement of the charm production in the forward region. And okay, it is fair to say that there were hints from from several experiments, in particular from all the open charm experiments in PP at fixed target, but no conclusive result. At Collider, and this you see here in this plot, this contribution is pushed to rapidities which are of the order of 6-7 units, and so it's practically impossible to be measured. On the contrary, when one goes at fixed target, this becomes closer and closer to mid-rapidity, and so it might eventually be detected, and one could, let's say, finally answer this question on the existence of this contribution. At low square root of s and studying proton lead, which is among the goals, as I mentioned, of the NA60 plus experiment, one could indeed look for signals of this effect. These are preliminary calculations, and Ramona stressed to me that I should explicitly say that these are preliminary. These are calculations of the effect of intrinsic charm, which should change a lot, for example, the shape of the RP LED when the studies is performed as a function of rapidity. Of course, let's say the implication is that if these kind of mechanisms exist, it should be detectable, especially at low SPS energy. Couple of slides on going still, let's say, lower in energy. This is CBM that might study threshold production. As you probably know, for for gold-gold collision, the J-psi production could occur only below the threshold for the elementary collision, which could, however, be, let's say, passed when studying lighter nuclei, while, of course, for PP and PA, one is beyond this threshold. This is, let's say, kind of a very difficult measurement. The interaction rates for NA60 plus that one foresees are 200 kilohertz, and here one has to go to 50 times higher in order to be able to see something, and that, okay, implies that indeed experimental, from the experimental point of view, this is a non-negligible kind of enterprise. Here some physics performance results which show a rather good statistics for gold-gold, a more limited statistic for p-gold. But let's say in any cases, and particularly in proton nucleus, the signal should be very clean, and so also even a lower statistics could allow to extract meaningful results. A few words on excited charmonium states. These were indeed observed also by NA50. Here you see again it has measured over expected ratio the J-psi results from NA50 compared to the psi2s results, and one could see a clear ordering in the suppression when moving from one to the other. So this can indeed be considered as the first discovery of sequential suppression, which was later very nicely confirmed by CMS in the upsilon sector. Clearly here the difficulty is that that one is lower by a factor, okay, maybe 50, not 100, but okay, the psi2s has a much smaller branching ratio. These results were obtained, let's say, by using a reference which was not obtained at the same energy of the nucleus data, and so let's say there is a bias due to that. But let's say this relative difference in the suppression strength, of course, is independent from this specific consideration. Okay, this I can skip and show you just some prospects for the psi2s measurements in NA60 plus. Again, due to the fact that this is not, let's say, that the yields are much lower, the uncertainties consequently increase, and so it might, let's say, seems feasible to have this measurement with the projected length of data taking down to about 100 GeV, while going lower in energy would need an extension of the beam time or maybe a thicker target or even larger intensities, which could be difficult to obtain. One word on the Chi-C measurement. This is always considered as a very interesting resonance in the game, but let's say honestly it was not measured until now. Not even at the LHC nuclear collisions. We start to see something now from LHCb in proton nucleus. These are results from HERA B, which were interesting because they showed similar strength of nuclear effects between the between the J-psi and the Chi-C. It's a highly non-trivial measurement, and it would be interesting to repeat these also at lower energies with more accuracy. So I come to quickly to the conclusions. What I wanted to show you today is that the charmonium measurements in nuclear collision have provided in the past both a first evidence for J-psi suppression beyond cold nuclear matter effects and a clear ordering of J-psi and psi-2s suppression according to their binding energy. The proton nucleus results have shown that, let's say, there is a superposition of various effects which become increasingly important at small collision energy, while no information exists below top SPS energy for any of these studies. So there are very good prospects for measurements to be carried out at low SPS energy, and the NA60 Plus project is studying an experiment to do that with a letter of intent and proposal to be prepared in the next year for what concerns the letter of intent, while in the threshold region, CBM could be exploring the production of quarkonia. So the aims can be different, but I mentioned two of them. So one again is detecting a threshold for hot matter effects on charmonia and correlate them with the temperature, which can be accurately obtained via studies of thermal dimuon production. And also maybe if we search evidence for new effects like intrinsic charm that if existing could find a good region to show up in this low SPS energy range. And with that, I thank you.
Thank you, Enrico. Thank you, Enrico. So do we have questions remotely? I don't see hands, but maybe it's too. I will play a bit. Do we have questions in the audience? I have one in case. I go? You go? Go. Giuseppe.
Enrico, you mentioned the normalization of J-psi to charm cross-section. Do you have something more? Is this total charm cross-section foreseen to be measured? Or,
yeah, in a sense, yes, because with this hadronic charm, one could access both the mesons, the D0, D plus DS, and the lambda C. The other, let's say, states heavier would be less
and
important.
The coverage in rapidity, with respect to the coverage in rapidity.
Yes, no, it's total in the rapidity region, basically between 0 and 1. So between 1 unit of rapidity, which at that energy is already a significant part of the coverage, especially when you go very low in energy. But yeah, it's not over the whole rapidity.
Okay. No question for us. So I sneak mine. So if you go back to the psi prime and psi, very beautiful plot from NA50. So you motivated part of NA60 Plus with looking at the onsets for the psi2s and the Chi-C. So the onset of the psi2s, I think we already know where it is, thanks to NA50, right? What are the possibilities for the Chi-C in NA60? I mean, you didn't show a performance plot for that.
Yeah,
it's
feasible.
Do
not exist for the moment, so this I did not see. For the onset of the psi2s here, let's say this was seen as, let's say, the psi2s also has a very likely an effect from the hadronic phase. Yeah. And this is true at all energies. So it's, let's say, first of all, of course, it's not so quantitatively important on the overall, let's say, business. It's a bit less than 10%. So so this is let's say a contribution that can be studied, but it will be relatively not important. The aim here would really be, let's say, with the J-psi, where let's say the statistic would be higher to observe the disappearance of the anomalous suppression effect.
But I really think if you can do the KC, it's the most interesting thing, right?
Would be, of course,
because
great.
I mean, if we think of, sorry for the ones who are remotely, but if you think of fit down, the start of the J-psi should be at the same place of the fit down, but the psi2s is only 10%. The KC is at least 20%. So if you had the KB on this picture, that would be very lovely.
This is something, that
look for it
would be great, but not trivial. Yeah.
Okay, do we have other questions remotely here? So I guess we're on time. Thank you, Enrico.